Hello everyone, and welcome to this talk about the work Finding Phish in a Haystack, a pipeline for phishing classification on certificate transparency logs. My name is Vincent, and this research is a collaborative effort of Drichel, myself, Justus von Brandt, and Ulrike Meyer. So, as the title suggests, our research focuses on phishing websites. Phishing attacks still pose a threat to general users on the internet, who are affected by loss of money or their online identity, as well as whole organizations where phishing attacks often help establishing a foothold for further attacks. Currently, the most popular methods of fighting phishing attacks are so-called block lists, which contain all known and active phishing websites and prevent users from visiting them. These block lists have a problem, however, as there's a short time span between the creation of a phishing website and its inclusion on a block list. Attackers, of course, have been known to use this window of opportunity to the fullest advantage, aiming to lure as many victims to their websites within the first few hours as possible. The aim of the research that I will present today is to reduce this window of opportunity by detecting possible phishing attacks before they are initiated by the attacker. In particular, as you can see on the figure to the right, phishing attacks typically start with the preparation step, where attackers, for example, set up their website. Only after the preparation is complete do they start executing the attack, in other words, send out phishing messages and so on. Typical detection approaches only activate at this second step, as they cannot detect potential attacks before they are executed. The approach discussed in this talk, on the other hand, aims to detect attacks in the first step already. This can be done by analyzing certificate transparency log data, or CT logs for short. CT logs are public, append-only logs that contain certificates of all websites that should be generally accessible. This property is enforced by popular browsers, for example Google Chrome and Safari, that only accept a certificate as valid if it is included in these logs. As such, if an attacker requests a certificate for their website, it will be visible in the CT logs and can be detected. The idea is therefore to monitor the logs for malicious certificates and flag potential phishing websites before the attack is executed, thus shortening the gap of opportunity for attackers. Now, the idea of using the information present in certificates to detect phishing websites is not new. Several classifiers have been proposed that make use of features included in a website certificate. These early classifiers, however, were designed to classify websites, not certificates, and are therefore less constrained in the available information. In particular, they make use of additional information, for example, the full URL or website content, in addition to the certificate, which is not possible in the CT log classification scenario. With increasing adaptation of the CT logs, several researchers have started designing classifiers specifically for the CT log use case. Here, the earliest phishing classifier, to our knowledge, is the Phishing Catcher, a tool that is published on GitHub and that uses expert knowledge to detect suspicious certificates. Another recent example is the classifier by Sakurai and co-authors that learns patterns in domain names of non-phishing websites, which can then be used to find new suspicious domain names. Even though these classifiers achieve promising results, they lack evaluations on actual CT log data, in particular in a live classification setting, where certificates are analyzed as soon as they are added to the logs. This is due to the fact that CT logs contain massive amounts of certificates, which complicates the interactions with these logs, including tasks like ground truth labeling. As such, the contribution of our work is the creation of a pipeline that can be used to train, evaluate, and compare classifiers on actual CT log data, including a live classification option that facilitates the early detection of phishing websites via certificates. In the following, I will explain the design of this pipeline in more detail, followed by an evaluation we performed to test its capabilities. For our pipeline, we identified 4 main goals that we focused on in our design and implementation efforts. First, the pipeline should take care of handling the data processing as much as possible. In particular, this includes the creation of datasets for training and testing, as well as the ground truth labeling of CT log data for comparative evaluations. The second design goal focuses on the comparison of classifiers. The comparison of classifiers is important to get an understanding whether new approaches are actual improvements over previous work, and to identify approaches that might be feasible in a real-world setting. The third design goal is about speed and scalability. These are generally favorable properties for an evaluation framework, but are especially important in the context of classifying CT log data, due to the size of the logs, which can grow at the speed of thousands of certificates every minute. Finally, the fourth design goal is modularity and extendability. As we made the source code publicly available, we wanted to make sure that it is relatively easy to extend and change the pipeline to fit the diverse needs of the research community in future work. With these goals in mind, we then created the pipeline. The final pipeline is split into 4 main modules that each accomplish a specific task. Conceptually, first in the classification process is the database module. It handles the collection of data from various sources for training and validation purposes, including benign data from CT logs and phishing certificates from phishing URL feeds. These certificates are then filtered against lists of known benign and malicious domain names, resulting in a labeled dataset that can be used in the following steps. The next module is the training module, which, as the name implies, handles the training of new classifiers based on the labeled datasets. The trained classifiers can then be used to classify CT log data, which is supported in turn by the classification module. Here, several interfaces to interact with CT logs exist, mainly to classify certificates in real time, so as soon as they are added to the logs, or to classify log data from a specific time frame in the past for comparative evaluations. The output labels can then be used by the final module, the intelligence module, to evaluate the classifiers or perform additional post-processing steps, like taking screenshots of potential phishing websites for further analysis. In all, the architecture facilitates the training and evaluation of classifiers on real-world data in a parallelized and scalable manner. We tested the pipeline functionalities in an example evaluation, which I will describe in the following. First, we used the database module to create training datasets. Here, phishing URLs were downloaded from several URL feeds, like PhishTank, OpenPhish, and PhishStats, and the certificates of the websites using HTTPS were extracted. This certificate collection process was run for more than a year and resulted, after filtering and removing duplicates, in more than 50,000 certificates. A matching number of benign certificates was also prepared by downloading and filtering certificates from the Google Xenon CT logs. This could be performed in a much shorter time frame, as CT logs preserve their past state and can be analyzed retroactively. Using this dataset, we then trained and evaluated a number of classifiers. Note that the interface for these classifiers in training and even classification was originally somewhat different, but could easily be applied to the pipeline by small adapter classes. First, we directly adapted 2 existing classifiers from related work to our pipeline. These are the aforementioned phishing catcher and the classifier by Sakurai and co-authors. The phishing catcher is a rule-based classifier based on hard-coded choices, which were selected by domain experts, while the classifier by Sakurai and co-authors clusters domain names and turns them into regular expressions for classification. We also tested 2 types of new classifiers: random forest classifiers as a representative of traditional machine learning approaches, and recurrent neural networks as a deep learning architecture. The random forest classifiers work on features that were extracted from the information included in the certificates. Features that focus on the domain name, for example the length of the domain or the number of subdomains, were handled separately. The details of these classifiers can be found in the paper. The recurrent neural networks also take the extracted features from the random forest as input, but additionally receive the complete domain name, as they are able to work on strings, while the random forest is not. The network architecture is shown on the right, while the paper again contains a more detailed description. For both random forest and recurrent neural network classifiers, we trained and tested several classifiers. However, I will only report on the most successful versions of each in the following. Next, let's take a look at the evaluation results. For our evaluation, we classified all certificates added to the Google Xenon logs in the first week of May 2020, more than 20 million certificates in all. When classifying a certificate, each classifier returns a confidence score between 0 and 1, indicating the confidence in the classification result. Now, to compare the classifiers, we set 2 fixed false positive rates, 0.0001, which is shown on the left side and corresponds to roughly 2,251 benign certificates that are misclassified as phishing in our evaluation timespan, and 0.001 on the right. We then set the classification thresholds of the evaluated classifiers to correspond to these false positive rates and compare the resulting number of true positives. We decided on this measurement as it provides a way to work with the large amount of certificates in the CT logs and serves as a good baseline to directly compare the classifier's performances. Looking at the first case, the lower false positive rate of 0.0001, we observe the following results. As can be seen, the related work classifiers are in the lead, with the classifier by Sakurai and co-authors achieving the highest number of true positives. In contrast, the novel classifiers based on traditional machine learning approaches only achieve 55 true positives in the case of the best random forest we tested, and only 36 true positives for our recurrent neural network. This changes somewhat in the second case, where the false positive rate is set to 0.001. While the phishing catcher is now clearly in the lead with more than 1,000 true positives, the recurrent neural network takes second place with 366 true positives, followed by the random forest and Sakurai classifiers. Note, however, that the first case is arguably a more useful measure of real-world applicability, as it creates significantly less false positives. Still, it seems that as of now, none of the classifiers achieve usable results with our training datasets and validation ground truth, as they still produce far more false positives than true positives. So, why is this the case? There are several possible reasons for the classification results. First, there are problems that are specific to our evaluation setup. We know that the filtering of our datasets could be improved. Here, we try to remove known benign certificates from the phishing dataset. However, this is not a trivial task. Phishing websites are often hosted on compromised infrastructure and might therefore also make use of a benign certificate. It is probably impossible to detect these kinds of phishing websites using CT log data, as the certificates were originally requested for a benign website. Next, our validation ground truth is not complete. We currently incorporate several intelligence providers into the pipeline to improve the labeling as far as possible. However, it is likely that some phishing websites were missed. This would convert some of our false positives to true positives, thus potentially increasing the true positive numbers in our evaluations. Still, we do not expect these wrongly labeled positives to make a significant impact compared to the number of benign websites, as we also later performed a review of the classifiers for false positives and did not find large numbers of obvious problems in the ground truth labeling there. As for our classifiers, we did not spend a lot of time optimizing the classifiers and trying different approaches for our evaluation, as the focus was on implementing the pipeline. It is most likely possible to increase the performance of machine learning classifiers by trying new approaches and optimizations. We also did not change the classifiers from related work, even though a close review of the rules generated by the classifier by Sakurai et al. And hard-coded into the phishing catcher might also improve their performances. In addition to these specific problems, we also note a number of problems that are inherent to the classification of CT log data in general. Here, the first problem is again the classification of phishing websites hosted on compromised infrastructure. As mentioned before, it's unlikely that these websites can be generally detected by CT log analysis at all. Next, phishers might start hiding information in the subdomains of their domain names. This approach, combined with using wildcard certificates, might also circumvent the analysis of CT logs in general. However, both of these approaches might also make these websites more suspicious to users who take a look at the URL, and thus making them less effective in general. Finally, websites that do not use HTTPS cannot be detected either. However, these websites also lack a certain element of legitimacy, as most major browsers will warn a user who is about to enter a password on a non-HTTPS website. In all, there's certainly some room for improvement in both datasets and classifiers to fully claim the potential of CT log analysis for phishing website detection. However, if we take a look back at the original design goals of the pipeline, we find that the pipeline can help tackle these problems in the future. We have shown that data processing from different sources, like URL feeds and CT logs, is possible even if the filtering of the datasets and validation ground truth might be improved in the future. We were also able to compare a diverse set of classifiers with different foundational approaches, fulfilling the second goal of the pipeline. Speed and scalability were, in our opinion, at a satisfactory degree as well, as the pipeline is highly scalable. In our tests, we were able to process weeks of data in several hours on highly parallelized hardware. The last goal, modularity, was somewhat more complicated to measure in our evaluations. Still, we focused on modularity in the design and implementation process, and at least were able to show that the pipeline fits the requirements of different types of classifiers. As such, we argue that the pipeline is well equipped to solve or at least improve on most of the specific problems mentioned before. With that, we are nearing the end of this talk. Here are the references used throughout the presentation. And to conclude, we created a pipeline to facilitate the classification of malicious certificates on CT logs. The pipeline supports the training, evaluation, and in particular comparison of classifiers. Even though our first evaluation results show that current classifiers still require additional work to be usable on real-world data, the pipeline itself should be able to handle these future challenges. The source code for the pipeline is publicly available on GitLab, and we hope it helps in working with CT logs in the future. Thank you very much for your attention.